Okay, thank you very much for inviting me to speak. So I'm going to talk about some things relating to the Zilber-Pink conjecture for abelian varieties. Um, and I'll start off by explaining what that conjecture is, some of the motivation for it, uh, and then what's known about it. Then I'll say a bit about why I'm interested in using G functions to try and say something about it, and what we can actually say. So one thing is I'm going to be interested in effective height bounds. And when I say effective in this talk, I mean in the sense that in principle there exists an algorithm that could compute height bounds or could compute a set of points. I'm not actually thinking about an algorithm, whether it will run in any reasonable amount of time or not. I've got some abelian variety over the complex numbers, and I've got an irreducible subvariety V in that abelian variety, which I put this condition is not contained in any proper subgroup of G. So the way that I think about this condition is if V was contained in a proper subgroup, then I should use that subgroup as my G instead. I've sort of had taken the wrong G if V was contained in some subgroup. So we take this generic V, we look at the union of all the algebraic subgroups whose codimension is strictly bigger than the dimension of V. This is what we call the unlikely intersection condition. So this says that it's unlikely for V to intersect one of these subgroups. And the conclusion of the conjecture will be that the intersection between V and this countable collection of subgroups is not Zariski dense in V. So this was motivated by a theorem of Bombieri, Masser, and Zanier, which is the analogous result where instead of an abelian variety, we take a power of the multiplicative group. And Bombieri, Masser, and Zanier proved this theorem under a few additional conditions. So the variety that you're trying to intersect with had to be a curve. It had to be defined over the algebraic numbers and not contained in any translate of a proper algebraic subgroup. So this is a stronger condition than being just not contained in a proper algebraic subgroup. Perhaps I should say, when I say proper algebraic subgroup here, the word proper, I mean in the sense of it's a strict subgroup. I don't mean that it's compact. And it's allowed to be disconnected. So there can be components that are sort of translates by torsion points, but in the Bombieri, Masser, and Zanier result, V was not contained in any translate by any element of the group of a proper algebraic subgroup. And later on, these latter two conditions were removed. That was due to Bombieri, Masser, and Zanier again for the removing the defined over Q bar condition, and due to Morin for removing this not contained in a translate, a proper algebraic subgroup condition. So that's one place that this conjecture was motivated from. Other motivation for this conjecture, I suppose Zilber's motivation for proposing this conjecture, why it has his name attached, is that it had links to Chanuel's conjecture and the model theory of the exponential function, or maybe in the case of this abelian variety version, the model theory of the exponential functions of abelian varieties. And then a further motivation is that it implies the Manin-Mumford and the Mordell-Lang conjectures. So the Manin-Mumford conjecture is the version of this conjecture where you intersect with subgroups of dimension 0. So that's just torsion points. The fact that it implies the Mordell-Lang conjecture is slightly less obvious, but is true, and is, I guess, an important reason for being interested in this conjecture. What do we know about this conjecture? It was proved by Habegger and Pila when the variety V is a curve, and both the abelian variety and the subvariety are defined over Q bar. And then it was later proved by Barrow and Dill, still when V is a curve, but now allowing the variety and the subvariety to be defined over the complex numbers. And the proof of Barrow and Dill deduces this fact over C from the Habegger-Pila theorem over Q bar. So there's still sort of an arithmetic core to how this is proved over Q bar. And for the rest of this talk, I'm going to stick to talking about things that happen inside these conditions. So I'm going to talk about effectivity, specifically when V is a curve and things are defined over Q bar. So how did the theorem of Habegger and Pila get proved? There were, I think, two major ingredients in this proof. One was counting rational points in definable sets in a no minimal structure. So that's using the Pila-Wilke theorem and this method of applying O minimal structures to solve Diophantine problems of this type was due to Pila and Zannier, who first used this method to give a new proof of the Mann and Mumford conjecture. And then the arithmetic ingredient, or at least a major part of the arithmetic ingredients, come from the bounded height theorem of Raymond. So in the original version of Habegger and Pila's proof, both of these two steps, 1 and 2, were ineffective. So the O minimal point counting parts, what I've labeled as part 1 here, can now be made effective using more recent developments in effective O minimality. But that's not the part I want to talk about in this talk. I'm going to talk about the bounded height aspect. So let's just state Raymond's bounded height theorem. So we're in exactly the same setup. We've got an abelian variety. Now we're restricting over Q bar. We're restricting to a subvariety which is a curve, and again, not contained in any proper algebraic subgroup. We look at the union of all algebraic subgroups of codimension at least 2 is now the condition because we've restricted to talking about a curve. And the conclusion of this theorem is that the intersection between C and all these subgroups has bounded height. So if the Zilber-Pink conjecture is true, which we know it is, then this would follow from that, because this is precisely the set that the Zilber-Pink conjecture asserts is finite. So Zilber-Pink conjecture set in general is not zeroistically dense, but when we're talking about curves, that means the set is finite, which obviously implies it must have bounded height. In the converse direction, is not immediate that bounded height implies finiteness here, because it's not at all obvious that the points in this set have bounded degree over Q. So that's not an immediate consequence of Northcott's theorem, and that's where the O minimal point counting came in. So this theorem of Raymond is also ineffective. The proof of the theorem is based around Voita's method for proving Mordell-Lang. And I'm not able to say anything effective at this level of generality. What we can say is, under the restriction that I mentioned earlier, if instead of considering being not contained in a proper algebraic subgroup, if we restrict to saying not contained in a translate of a proper algebraic subgroup, then there is an effective theorem, also due to Raymond. So in fact, a slightly older theorem of Raymond said that when C was not contained in a translate of a proper algebraic subgroup, then you still have bounded height, and this is in principle effective. The proof of this theorem relied on the Manin and Demyanenko method, which is based around the Weyheit machine, properties of Néron-Tate heights. And I think while, as I say, it's effective in principle, I think it's quite hard to be explicit in this method about how the bounds you get depend on the curve. And I should say that this restriction to being not contained in a translate of a proper algebraic subgroup is a very serious restriction, in that I originally said the Zilber-Pink conjecture implies Mordell-Lang, but when we impose this condition about not contained in a translate, it no longer implies Mordell-Lang. So we don't get an effective Mordell-Lang theorem out of this. Right. There is another case, or a special case of this theorem, which is much more explicit. So due to Viada, and then later improved by Veneziano and Viada, and this was building on earlier work by Ciccoli, Veneziano, and Viada, gave explicit bounds for this height in the case when the abelian variety G is a power of an elliptic curve. Again, this was under the condition not being contained in a translate of proper algebraic subgroup. So again, avoiding sort of saying something very general about Mordell-Lang. But still, they explicitly describe how the bounds depend on the degree of the curve, the degree of the base number field that everything's defined over, and the height of the curve. And this used arithmetic intersection theory and the geometry of numbers as the methods in its proof. Right. So I guess I want to say that the theorem I'm about to state is not new in the sense that it's contained within the theorem of Raymond that I've already stated, or it says something weaker, but it's proved using this different method of G functions. And I'll explain in a moment why I think it's interesting to try and understand what you can do using G functions. That was sort of how I came into this project, was to ask, what can you say about this theorem using the method of G functions? So, I thought I was going to say there. Okay, so well, maybe I should explain why trying to use G functions is an interesting thing to do here. So G functions, which I'll define in a few minutes, are a tool that has been used to prove height bounds for the fibers in some family of abelian varieties which have extra endomorphisms. And this sort of forms part of the Zilber-Pink conjecture for Shimura varieties, in the same way that I've been talking about the Zilber-Pink conjecture for abelian varieties, and having some height bound that's a key step in proving that. Similarly, these G functions prove a height bound that's a step towards proving cases of the Zilber-Pink conjecture for Shimura varieties. And in this context of talking about endomorphisms in families of abelian varieties, this was an idea of André, and in the past few years, there have been results of this type by a number of different people, by Bignamini and Masser, who used it to get an effective André Oort in a certain setting, by Daw and myself, Papas, Urbanic, Yuel, who all considered different types of endomorphism conditions that you might put in families of abelian varieties, and maybe also some generalizations to things like families of Hod structures. So that's why trying to use G functions to prove height bounds sort of in the context of the Zilber-Pink conjecture was an interesting thing to do, and why I wanted to see what could you do in the perhaps generally easier case of the Zilber-Pink conjecture for abelian varieties. Okay, so this is the theorem that you can actually prove using G functions. And this is in the same sort of setup that we've had before, but there are several additional conditions that make this weaker than the theorem of Raymond that was stated before. So, firstly, the abelian variety that we consider is now going to be of the form a power of some fixed abelian variety. I probably want to insist actually that my A here is simple. So I feel like this is not an entirely serious restriction in the sense that if you've got an arbitrary abelian variety, then up to isogeny, you can factorize it as a product of powers of simple abelian varieties. And then whenever you look at a subgroup of G, it's going to be up to isogeny a product of subgroups in each of these powers. And they sort of can't really interact with each other from a subgroup point of view. So that means that proving theorems for this case is a major part of proving the theorem in general. But you get a much cleaner statement for what I can actually prove by just restricting to this case. So that's why I think that restriction is not so significant. On the other hand, what is a significant restriction is that we now have this condition that the 0 point of my abelian variety has to be contained in the curve. So, I mean, this is not a completely crazy restriction in that, for example, if you've got a curve with a rational point on it that you know already, and you embed it in its Jacobian, you can naturally get a curve that satisfies this 0 contained in C condition. But it is still, from some other points of view, if you don't have a rational point lying around already, for example, this is a serious condition. And you'll notice that the way that I've stated this theorem, I haven't put the not contained in any translate condition, but actually the combination of these two, not contained in any proper algebraic subgroup and containing the 0 point, these do imply the not contained in any translate. Or a subgroup. So this really is a stronger condition than was in the previous effective theorem of Raymond. The other thing that I think is a very serious restriction is that here we have codimension bigger than this pretty big number, where we want to have codimension greater than or equal to 2 here, and we've got something that's pretty huge compared with that. And that seems to be fundamental to the method. Hopefully, if I have time, I'll eventually point out where this comes from. This is why I put very unlikely intersections in the title of my talk, because the codimension is much bigger than what you would need just to be an unlikely intersection. And then the final way that this theorem is weaker is the bound that you get at the end says this height is less than some polynomial in the degree of the field on which S lives, where previously you just had this height was less than or equal to a constant depending on A and C, obviously. At the same time, this is maybe not so serious a restriction in the sense that this is enough to make the point counting argument for deducing Zilber-Pink work. And therefore, if you have a bound like this, you can put it into all that minimal machinery and get out a proof that this set is actually finite. And therefore does have completely bounded height. And I suppose if you do the minimality effectively, then in principle you get out at the end an effective algorithm for computing the entire set of points. Okay, so those are or the ways that this theorem is weaker than what we had before. Now I'm going to talk about what we do using G functions to prove this theorem, and where especially this condition comes up from in the end. So what is a G function? A G function is a power series whose coefficients are algebraic numbers, and it has to satisfy a linear differential equation with coefficients in rational functions over Q bar, and it satisfies a growth condition on the coefficients at all places of Q bar. So another way of saying that would be it satisfies a growth condition for the absolute values on all the embeddings of Q bar into C, and it satisfies a growth condition on the denominators, the coefficients. That takes care of the finite places. And so examples of these things, well, maybe one simple example that I can write down is log of 1 plus x. So that's, I can never get the signs right in this equation. Is it something like x minus x squared over 2 plus x cubed over 3? Yeah, I may have got the signs wrong, but this is some power series. And a much more general class of examples, which I suppose includes this one, is that if you consider an algebraic curve defined over Q bar, you take some differential form. So if you wanted to get log, you take dx over x, I think. You take some base point in Q bar, and then you look at the integral of this differential form from that base point to wherever else, and this is a G function. Or so speaking more precisely, a G function is supposed to be a power series. So what I mean is you take this integral, you take its Taylor series in terms of some local parameter around your base point. And this idea was due to Siegel. Siegel gave this as an example originally when he defined them, and this happens to be the example, the G functions that I'm going to want to use in order to prove something about unlikely intersections. Okay, so what can we do with G functions? The main thing is this theorem, which is due to Bombieri with some additions due to André. And so I suppose the way to think about this theorem is we'd like to say something about the transcendence of values of G functions. So proving that sort of naturally occurring numbers are transcendental or even algebraically independent is hard. And so what this theorem does is it doesn't prove that. It proves that there's some restrictions on the types of algebraic relations that can exist between certain numbers that you might expect to be transcendental. So you take some collection of G functions, you evaluate them at some algebraic point, and if these evaluations satisfy a non-trivial global relation, and I'll say what these words mean in just a minute, but if you have this polynomial relation, coefficients in Q bar that's equal to 0, then you get a height bound on this point psi. So, as I say, you sort of maybe hope to try and prove that some numbers are algebraically independent. That would be saying there don't exist any p's like this at all, that you put these numbers in and get 0. But you can't prove that. What you can prove is you can get a height bound on the size. So what do the words non-trivial and global mean here? So non-trivial means that this P does not come from a polynomial relation between the power series themselves. So if I gave you power series like y1 equals x and y2 equals x squared, that's a pair of power series, and you won't be surprised to find a polynomial relation between their values at any point, because there's a polynomial relation between the power series that we started with. There are a few tricky details in saying precisely what I mean by comes from here that I'm going to ignore. But yes, if we want to get any sort of reasonable theorem like this, we need to rule out the relations that exist as relations between the power series themselves. And then what does global mean? So maybe before coming to the definition of global, we should just think for a moment about what does it mean when we write y1 of psi, where y1 is a power series with coefficients in q bar, and psi is an algebraic number. So evaluating a power series is an analytic process, not an algebraic one. You have to sum some infinite series. So that means you want to do it in a complete field and not just in q bar. Indeed, you expect that you quite likely get transcendental numbers out. So in principle, you might attempt to do this in any completion of q bar. And sometimes you'll succeed, sometimes you won't, because there, of course, there'd be a radius of convergence of this power series in each completion of q bar. And you can do this evaluation if the absolute value of psi in that completion is less than the radius of convergence of y1 in this completion. So when we say that we have a global relation here, what this means is that the condition that this polynomial vanishes has to hold in every completion of q bar in which it makes sense to evaluate the relation. So every completion in which the absolute value of psi is less than the minimum of all these radii of convergence. And also less than 1, that's just an additional point that turns out to be quite convenient. So this might seem like I'm talking about an awful lot of completions of q bar. Of course, you could restrict your attention to just thinking about a single number field. So it follows from the definition of g functions that the coefficients of any given g function all lie in some fixed number field. So I could pick a number field k that contains the coefficients of all my g functions and contains psi and contains p. And then I just have to say in every completion of that number field, which is at least a slightly easier thing to think about than every completion of q bar. Right. So this is the theorem that André used originally in first thinking about applying g functions to families of abelian varieties. This is a theorem that we're going to use when we apply them to a curve in an abelian variety. And now let's talk a little bit more about how we set things up in order to apply this theorem. Yes, I should have mentioned, since I'm interested in effectivity, we need to point out that this theorem is indeed effective. So given suitable information about your g functions, things like what are their radii of convergence, and about their differential equations, things like what are the singularities of those equations, then you can explicitly write down the height bound on the point psi that you get. Okay, so how do we set this up? We take some abelian variety, and I'm going to write d for the dimension of my abelian variety A. I'm going to consider my curve to be contained in some power of A, as I said in the theorem, and I impose this condition that 0 is a point in the curve. I'm going to write P1 up to Pn for the various projections that we get now from the curve into my simple abelian variety A. And I'm going to pick a basis for the holomorphic 1 forms on my abelian variety A. So the number of holomorphic 1 forms on an abelian variety of dimension d is equal to d. And then the g functions that I'm going to consider will be the integrals. So I pull back my one forms to the curve, and I take all the different ways I could do that. And this gives me some collection of functions on the curve. And then these functions, or more precisely their Taylor series, are the g functions that I'm going to consider. So I've got I going from 1 up to n here, and j going from 1 up to d. I've got n times d g functions that I consider. And I needed the 0 in the C because I needed to pick some base point that I was going to expand around, basically. And it will matter a little later on that I did pick the 0 of my abelian variety as the base point. So our goal is going to be to prove that if we've got some point in our curve Q, in our curve C, which is contained in an algebraic subgroup of large codimension, sort of the large codimension that I wrote down earlier, then we want there to be a global relation among the values of these g functions at that point. And then we'll apply the Bombieri and André theorem to get a height bound for those points. So I guess the first thing to take care of is we need to make sure the relations we get are non-trivial, but that's very easy in this case. From our condition that C was not contained in any translate of a proper algebraic subgroup, there aren't any trivial relations. This is the Accianual theorem, essentially says that these functions are algebraically independent as functions. Okay, so how do we go about building a global relation that satisfies these conditions at every place of some number field? What we do is this is a standard strategy for doing this. We can find one relation that works for all the non-Archimedean places, or at least all the non-Archimedean places where our g functions converge at the point we're interested in, since that's what we needed to get a global relation. And then for the Archimedean places, we separately find a relation for each Archimedean place. And then we just multiply all these together. So it mattered that we had a single relation for all the non-Archimedean places, because of course we don't want to end up trying to multiply together infinitely many polynomials. That won't give us a polynomial. But here, we only have finitely many things to multiply together. I guess that's relying on the fact that I don't really need to work with all completions of Q bar. I just need to work with all completions of some number field that's large enough to contain all the things I'm interested in. And in particular, when I take these Archimedean places here, this is of some field where I guess A is defined, C is defined, and the point S that I'm interested in is defined. So the number of Archimedean places that I have to consider here is the degree of this field, which of course up to, so if I regard A and C as fixed, but I allow this point S to vary, then this is proportional to the degree of my field Q, and it's from here that the dependence on this degree comes up in the height bound that I get out at the end. So let's talk about how we find these relations at non-Archimedean and at Archimedean places. So the non-Archimedean ones are simpler. Okay, we work in some non-Archimedean completion of this field that I just mentioned. If we've got this point S in some proper algebraic subgroup of G, remember G was equal to A to the N, then this implies that I can describe my subgroup by some condition like this. I guess if I want to describe an arbitrary subgroup, I might need multiple conditions like this, but at least the point S must satisfy at least one condition of this form. So I take combinations of the projections onto all the factors where I can sort of multiply by endomorphisms of my abelian variety. And in the non-Archimedean places version of this, all I need is going to be this has to be contained in a proper algebraic subgroup. In this non-Archimedean world, I don't care about the codimension. So I get something much stronger in this situation. But in the end, of course, we're going to need to care about the Archimedean places as well. So I think in principle here, these coefficients can be endomorphisms of my abelian variety A, which since A was simple, this is some division algebra. But in order to simplify the exposition here, I'm going to assume that these are all just integers. This doesn't make a major difference, but it will just simplify the explanation in this talk. So maybe end A was the integers, maybe it wasn't, but they happen to be in Z. Okay, so what can we say? So this function that sends points to integrals of differential forms on the abelian variety is a group homomorphism on some neighborhood of the origin. This is basically because these integrals are the formal logarithm of the formal group of the abelian variety. And we know that over p-adic fields, formal logarithms of formal groups are indeed homomorphisms on a suitable disk. So this is where we use the fact that this had to be a non-Archimedean field to get that this formal logarithm is actually a group homomorphism. So if we take this relation and we apply this group homomorphism, which essentially are our G functions, then we get some relation among the values of the G functions that comes out. And this relation, this is independent of the non-Archimedean completion that I picked, because this relation here was purely an algebraic thing that happened over the number field that we started with. So I suppose if we didn't have the restriction to the coefficients being in Z, then we'd need to sort of modify this a little bit to make use of the fact that these endomorphisms act on the differential forms. And at least if we make our number field big enough that all the endomorphisms are defined over K, we'd get a K-linear action. It would be independent of what completion we worked in, and we'd get some relation out at the end that was independent of the completion. So that's the non-Archimedean places where we can sort of do this quite quickly, and we don't need, we only need to be contained in a proper algebraic subgroup of any codimension at all. Now let's go to the Archimedean places. So what happens here is that over the complex numbers, this integral is no longer a homomorphism on some neighborhood of the origin. It sort of wouldn't really make sense for it to be a homomorphism on a neighborhood of the origin because the complex points in an abelian variety don't contain simply connected open subgroups. But what we do get is that it's additive up to periods. So I suppose this is also sort of like the fact that p-adically log is well behaved. That's what we saw before. Whereas in the Archimedean world, it's the exponential function that's better behaved. And here we still need to talk about log because these integrals are morally logarithms on our abelian variety. So when we say it's additive up to periods, what that means is that this relation that we had saying that some combination of these points was 0, when we integrate that, we get that some combination of the integrals is equal to the integral of some loop. So these are the periods of these integrals. and they are, in general, transcendental numbers. Which means that what we've written down here is not a relation with coefficients in Q bar, as we'd like. But what we can say is that if we have a lot of relations that are all similar to this, the various different transcendental numbers that appear on the right-hand side will be algebraically dependent. So they satisfy these relations that are called the Riemann period relations for an abelian variety. So what this means is if we have a whole lot of relations that look like this, well, we can eventually take some combination of them in a way that sort of makes everything on the right-hand side disappear. I suppose the simplest example of this is if you have more than 2D plus 1 of these relations, then you can show that these right-hand sides will be linearly dependent. And then you literally just have to take a linear combination of the left-hand sides and get some relation equals 0. If you have this weaker condition, that this is more than, oh, I forgot to, yeah. Sorry, if there are at least 3 halves D plus 1 of these relations, then you have to do something cleverer. You don't get linear dependence, you just get an algebraic dependence. So you have to combine them in a fancier way. But again, you can ultimately end up with some polynomial in Fij is evaluated as equal to 0. And that's what we want to apply the Bombieri and André theorem. And in particular, it's this thing that we need lots of relations that look like this that give us our condition that the subgroups have to have codimension bigger than this thing. So maybe the difference between this 3 halves D plus 1 relations and this codimension having an extra factor of D here is because the dimension of my simple abelian variety A was D already. So when I say the codimension is at least this, that means that I've sort of got at least this many copies of A that I've killed off in the subgroup. So this is the number copies A in, I guess, in the quotient by the subgroup in which S lives. So if I have this codimension subgroup, I get this many relations of this form. It should be possible to improve this slightly. So this is something that I haven't done yet, but it should be possible to improve this to roughly D times D plus 1 as the codimension, maybe D times D plus 2. This would be that I've only talked about using holomorphic differential forms. We could use meromorphic differential forms. So forms of the second kind, as well as the holomorphic ones. And that's a little bit more complicated because you no longer get things that are homomorphisms up to periods. There's a more complicated addition formula for the integrals of these meromorphic differential forms. But it shouldn't make a huge difference. So these numbers, the D times D plus 1 or the D times 3 halves D plus 1, using only holomorphic differential forms, you can check that you can't possibly do any better than these using this method, at least assuming the Grothendieck period conjecture is true. That tells you what the transcendence degree of the periods you get is going to be. And then from that, you can determine that this is the best you can do, at least in the case where end A is Z. I suppose if your endomorphisms are bigger than Z, you could be a little more clever about how you manipulate the periods and get a better bound. And the period conjecture should predict what that better bound is. Okay, I think I'll stop there.